So I'm Alex Sena, and I'm joined by Amit Kothekar, and today we're here to talk about human accommodations in space exploration and this idea of evolving beyond spam in a can. And so we're here on behalf of BLiSS, which stands for Bioastronautics and Life Support Systems. We're a human spaceflight group on campus doing a variety of different projects that we'll be talking about today. You can see our full team up in the upper right-hand corner in front of our space habitat mock-up that we'll be talking about a little bit later on. And the crux of what we're hoping to talk about today was summarized really well by Major Charles Berry, an Air Force physician in 1958, when he was one of the first people to propose the idea that the psychological challenges of space exploration might start to outweigh the physiological problems. And it's unsurprising that he said this right after the first test results came out from the space cabin simulator. So this was in the 50s, our first attempt at trying to simulate what we believe the inside of a spacecraft might be like. So a scientist isolated himself in there for 7 days and gave himself a series of tasks to measure his performance, and went from giddy and fun to functionally insane within the span of a few days. And at the same time, when recruitment for the first astronaut program was underway, and actually Air Force commanding officers didn't want their test pilots going and doing it because they believed it was a waste of their talent. They thought that at this point, humans were just spam in a can at the mercy of engineers who would just put them in a spacecraft and have them do nothing but breathe and produce heat. That's actually not too far off when you start to look at the first human-rated spacecraft, so Mercury for the United States and Vostok for the Soviet Union. Their life support systems were really just focused on what if you ignore, they will just die, essentially. This idea of thermal control or carbon dioxide scrubbing systems, this idea that you can't have carbon dioxide or heat buildup, so those are the only two things that they're addressing at this point. And they made use of something called an open loop life support system. So this is something to the idea that you're not regenerating, you're not recycling absolutely anything. Everything that you want to consume, you have to bring on board or you have to supply in some way. And all your waste products get dumped overboard or stay on the ship in some form or another. So no recycling of any sort. But then as life support started to get more sophisticated, we started noticing this ability to close the loops. So you can close an air loop, for example, by scrubbing your CO2 and reclaiming water and oxygen from that process. Or, for example, closing the water loop by collecting ambient humidity in the air or using wastewater and just purifying it, or even reducing it from CO2. And what you'll notice is that there's actually a lot of overlap in those systems, and you can join them together into a partially closed system in which everything is joined, where you're reclaiming water from your CO2 scrubbing processes, where your wastewater is used in those chemical reactions. And everything is linked in one environmental control and life support system, or just ECLSS. And so what this partially closed loop does is it actually cuts down that resupply mass by about 90%, in the sense that water and gas actually become some of the heaviest components, and all you have left is 10%, which is just food and waste products. And this is why the ISS makes use of this joint architecture now. So this diagram on the left and the diagram on the right are functionally the same thing, just with a few redundancies built in. On top of that, these environments that we're controlling are getting more and more Earth-like. So our first real long-duration space station, Skylab, actually only had a third of Earth pressure and significantly more oxygen, whereas now we're actually moving more towards almost an exact Earth-like environment. This also ties into the idea that we've defined a comfort zone. So in the high-level requirements, when you're designing any type of long-duration living environment in space, there's this defined comfort zone, which is really just a relationship between dew point, temperature, pressure, relative humidity, and all these terms that we now know optimize a crew's ability to work in space. So if you're going to create these habitats, we now have to stay within this zone focused on crew comfort, which is already a total departure from just keeping them alive and cold. And the key parameter when designing this stuff is the idea of kilogram per person per day. And that kilogram per person ties into kind of metabolic rates, the fact that we know that humans need to consume a certain amount of oxygen, food, and water, and they'll produce a certain amount of waste, carbon dioxide, and water as well. And reducing that kilogram per person comes in the form of closing those loops. So the idea that your water is being recycled, like look at the ISS rehydrates their food specifically so that they're only sending up dry mass and rehydrating it later with water that they've reclaimed. So slowly and slowly shrinking those mass balances and that mass flow. Like you can see in the diagram on the left, an example of an 8-person crew and how you manage the water mass. So at the end of it, when you figure out how everything's recycled, you know exactly how much of each system needs to be supplied and how much needs to be dumped, and that becomes your kilogram per person. Now, this interesting term is that also is per day, which means that the amount that you're going to need is slowly going to increase per day as you go on these longer and longer missions. However, what's interesting is that's not necessarily the biggest limitation. So when you think about a Mars mission, people like to think that it's just a much longer mission that's going to last hundreds of days, and that's what the biggest obstacle is. But we've lived in space for longer than Martian missions will take. Valery Polyakov stayed aboard the Mir space station for 437 days in 1995, and Scott Kelly and Mikhail Kornienko spent a year in space, most recently in 2016 aboard the ISS. But the reason they were able to do this is because they exist within the International Space Station's resupply architecture, where that kilogram per day is less of a concern when you can also send up a higher rate of supplies and get that 10% of food and waste products up and down on a regular basis. So that's not really where the problem lies in time. And you'll notice in this chart on the right, which plots complexity over the length of a mission, that the exponential growth comes from those two areas that we haven't closed a loop for. So food and waste are really where it gets increasingly and exponentially more complicated with missions, but the curve starts to flatten a little bit when you look at water supply, air revitalization, these processes that we have precedent and experience handling when it comes to life support systems. So that's where the work for BLiSS starts to begin. Our very first project in 2017 was the astronaut urine repurposing apparatus, which handled that waste recycling end of things, where we took liquid human waste and turned it into something usable for plants, both as water and for nutrients. Then we took that even further the next year in 2018, working on what we call the 3D substrate project. So this idea that dirt doesn't really function well in microgravity. You forget that it has to sit down in a pot versus just floating around as particles. So how do you 3D print a lattice that allows the roots to grow, and can you make that lattice out of nutrient-rich material? So BLiSS started working on this idea and was successfully able to create a design that grew radishes and lettuce that can be used in future spaceflight. Again, closing that food loop as we're able to generate more of our nutrients on board. Another problem that we didn't even get to touch on very much is that if you're spending longer time out in space, you're going to need more and more medical help. So the idea that there are things that are either totally routine or total emergencies that you need to be prepared for. So in 2019, the BLiSS group focused on building a medical architecture that can handle both routine and emergency operations, figuring out exactly what it would take to go out into deep space. So this architecture, we built a VR simulation for it that you can see on the right with a few of our members scanned inside of it. But this was a really cool analysis to do. Again, what does it take to get to longer missions out in space? A lot of our work has culminated in our 2018 project, which was the Argo mission. The idea for this was to design a habitat that could function both as a deep space transport as well as a space habitat. So this isn't something that goes through space and then lands on Mars, but rather a common layout that can function in both ways. This makes it so that the crew doesn't have to retrain or forget the layout of their habitat in the months it takes to get to Mars. If you're working in space in the same place that you're going to be working on Mars, then you're already familiar by the time you get down there. On top of that, the circular design rotates at 6 RPM, which simulates artificial Martian gravity. So the crew is slowly getting acclimated to the planet before they've even arrived. We got to build a full-scale mock-up of this in 2018 in the basement of the Space Research Building, as well as a VR version of the deep space configuration where everything is aligned against the walls rather than on the floor. And we recently refurbished this, and it's still in the basement, and we were able to announce the official creation of the Michigan Space Institute in front of it. So if anyone ever wants to check that out, it's in the basement of the SRB.
So long duration missions not only require us to close the loop when we're thinking about designing our habitats, but also they result in increased level of autonomy for the crew. And this autonomy results in some psychological stresses, which were investigated in the Mars 500 experiment. So this experiment is where 6 astronauts were in an isolation chamber for 520 days. And they were studied for how the environment impacted them, whether it was like seeing the same people over and over again or managing their own schedule and how that impacted their psyche. And it was seen that the increase in crew autonomy actually required a lot more awareness of the system and managing the system. And so bringing that complicated information to the astronauts without imparting stress is actually what brings human factors to the forefront of how to have a sustainable space presence. And this is actually what BLiSS has been working on. We've been designing a user interface for Gateway. Specifically, we've been looking at how to interface with technology-assisted autonomy. And while designing our user interface, which you can see on the right, we were looking at ways to have the astronauts stay aware and alert without overloading them with information and potentially stressing them out while they're really far away at the moon. And partly this was done through utilizing modern technology in order to increase user friendliness, such as through using touchscreen tablets and voice control to make it a lot more intuitive. We're seeing this trend also in EVAs as well. So currently, EVA tasks for astronauts are very engineering focused, and they're very sequential with an obvious goal at the end of it, or obvious result. But when we move to the future of exploring planets or other celestial bodies, the operations are going to need to have a lot more flexibility associated with them and room for people to think on their feet. And that's a big difference than what we've seen in the past with our lunar missions. And this is where BLiSS comes in again. We're looking to provide this flexibility with augmented reality solutions. Here you can see a mock-up of one of our other projects, which look to provide a user interface and prototype for augmented reality tools for astronauts during EVAs. And here on this layout, you can see how astronauts are able to actually provide or have a layout of different waypoints, create notes much more efficiently, listen to audio and video all right within their face. And that provides a lot more flexibility and allows them to move about their day much more efficiently and provide better results, hopefully. So we've been focusing a lot on space exploration, but what about space tourism? That's the new trend nowadays. And what we're seeing in space tourism is that there's actually a departure from what we've seen in the past with astronauts. So traditionally, we'd have astronauts going in suits for survival. They're just survival-based suits. But now the astronauts, quote unquote, you can see on the right from Virgin Galactic, the suits are a lot more comfort-driven. And also the passengers that are going up there have little to no physical or psychological training, which is also a huge difference that we've seen in the past, where our astronauts have been very military and Navy focused. With military Navy background. And also another interesting trend is that the passengers are no longer going to be in control. They're either going to be in a piloted craft or autonomous craft, but they're also still going to be required to be safe. So now we're seeing that shift in how humans are not going to be able to be required to be kept safe on their own front, but also through the design process behind that as well. So what's next? The early space missions provided the bare minimum for the crew. We just discussed how spacesuits, such as the one that Alan Shepard wore in the Mercury capsule on the left, you can see we're just providing for survival. But now in the future of space exploration, we're seeing a departure from that original spam and a cam idea. The humans are now actually the valuable crew. We can think on our feet, and we're looking to actually enhance the capabilities of our crew. And that's where BLiSS comes in. BLiSS is actually focused on solving the human-centered problems to enable long-term missions and hopefully have a habitat in space permanently. But in the end, we're actually seeing how space tourism is going back to that spam in a can idea, where the tourists are actually wearing suits that aren't directed towards survival, and they're not necessarily going out to achieve goal-oriented tasks, but merely just to look out at the Earth below them.
And so with that, we hope you can understand why BLiSS's motto is Domi Inter Astra, or Home Among the Stars, which is really that we're not just focused on learning how humans survive in space, but truly how they can thrive in space as well. As you get further and further away from your home planet, you have to bring more and more of the planet with you. And we're really focused on making those future spacecraft feel like home, even as you're traveling further and further deep into the cosmos. So we'd be happy to spend the rest of the time answering any questions. But that's really all that we have to talk about today. So thank you guys.
Thank you.